Okay, we'll wait for a few minutes for others to join. Okay, then let us start. I hope I'm audible to everyone. Can anyone of you confirm? Hello. Am I audible to everyone? Can anyone of you confirm me?
You are audible, sir.
Is my voice clear?
Clear, clear.
Okay, thank you. All right, so welcome to the week 4 tutorial for the course IC Engine and Gas Turbine. So in the previous tutorial, we started with the mean effective pressure and tended towards doing a few numericals. Today we'll start with the semi-diesel, or you can say dual cycle. Semi-diesel cycle. Or let me share my screen. I hope everyone is regular with their lecture videos from the given by the professor on the Nptel book. I hope my screen is visible now. Can anyone of you confirm? Hello. Am I audible?
Clear, sir.
Yeah. Okay, thank you. All right. So please let me know at any point of time if my voice breaks or you're not able to listen suddenly abruptly. The network goes off from my end. Please let me know. Otherwise, uh, if you guys won't be able to listen me and hear me. So I want you just be prompt, immediately pinpoint me out that so you're not audible. Please with your mic. Okay, thank you so much. So let us start with the dual cycle. I hope everyone is able to, I expect that everyone is able to see my screen and whatever I'm writing. So dual cycle or we also can call as semi-diesel cycle. Okay. Dual cycle or semi-diesel cycle. And this kind of cycle is basically used for diesel cars only. Okay. So here the fuel injected is diesel only. So in this cycle, basically what happens, speed is comparatively higher than the diesel cycle. Because in diesel cycle, torque was high for the same power output. Whereas in a petrol engine, the speed is higher and torque is less for the same power. So in the given diesel cycle, there is one additional process which is being employed is basically first you do the isentropic compression, then as per the Otto cycle you add the heat addition at the constant volume, then as per the diesel cycle you add the heat addition at constant pressure. So two times of heat addition is being done, one at volume, one at pressure. And then finally isentropic expansion happens and heat rejection at constant volume. So let me draw the cycle. So this is pressure versus volume plot. So here, if you see, we have from process 1 to 2, we have isentropic compression. Okay. Then from process 2 to 3, we have heat addition at constant volume. Then from 3 to 4, we have heat addition at constant pressure. Then we have 4 to 5, isentropic expansion. And finally, 5 to 1, heat rejection at constant volume. So here the heat is being added at constant volume. Here the heat has been added at constant pressure. And this will be your cutoff point again. Cutoff point. Okay. And this will be your explosion point. A new point has been, terminology has come, which is basically your explosion point. I'll explain all these terminologies. And let's just say, and this is heat rejection at constant volume. Heat rejection at constant volume. Okay. And what happens? This pressure in the cylinder is maximum at this point. P is maximum. All right. Let me write one by one for diesel cars. In this cycle, speed is higher than diesel cycle. Okay. Now again, and this is start of injection. I missed one point here. Start of injection. Fuel injection. Start of fuel injection. Okay. So these are the all the points and the arrows of the cycle. Clockwise. And it's a work producing device. So we generally mark it with the clockwise direction. You might have studied in thermodynamics. This thing. Okay, so first the terminology will be compression ratio. So compression ratio will be higher. Any process ratio is nothing but higher to lower. So it will be V1 over V2. So V1 is here. Okay. V1 is here. And V2 is at this point. V2 and V3 are same. This is V1 equal to V5. This is V1 equal to V2 equal to V3. Okay. This is your, let me use some. This is your clearance volume, VC. Okay. Then again, we are having some cutoff. Okay. Cutoff point is there. So we know that cutoff ratio, which we earlier defined for the diesel cycle, that will be RE. Sorry, the rho. The cutoff ratio. And expansion is happening from 4 to 5. The expansion will be RE. Expansion ratio will be from this to this. Or the swept volume is from, let me write. Am I audible? Hello? Has anyone joined? Let me see once. Okay. All right. So whatever I spoke was audible to everyone. Can anyone confirm me, please? Santosh?
Yes, sir.
Am I audible clearly? Whatever I spoke.
Yeah. You are audible, clear audible.
Okay, thank you.
Uh,
All right. So what I was saying in the last is that the compression ratio is from V1 to V2. Clearance volume we have made, the volume we have defined. Let us define all the remaining terminologies. Okay. So we were here at R V1 by V2. Now what will be the cutoff ratio? So this is compression ratio. Then rho, that is your cutoff ratio, that is from 4 to 3, from this position, 4 to 3. So that will be V4 by V3. And V3 and V2 are same. Okay, so both it is I can write. Rho is V4 by V3, or both are same. So this is cutoff ratio. Okay, cutoff ratio. Then expansion ratio is from 5 to 4 to 5. Okay, so it will be V5 by V4, expansion ratio. V5 by V2. So what is V5 by V2? V5 by V2. V5 is nothing but V1 because both are same again, and it can be V2 as it is. What is V4? V4, let us keep it like this, and V2 is again V3, right? V2 and V3 are this. So we know that V1 by V2 is compression ratio. Just now we defined compression ratio. And V4 by V3 is your cutoff ratio. V4 by V3 is your cutoff ratio. So we can say that our expansion ratio can be again written in terms of R by okay. All right. Compression ratio. All right. Now there is one another ratio terminology which has been introduced, that is your explosion ratio. Explosion ratio. Because I said that this is your explosion point. This is your explosion point, the point 3. So we can say that why explosion ratio is came here, because pressure at point 3 and pressure at point 2 is different. So it will be a ratio of the to pressures. Again, it's a process ratio, so higher to lower. As I told, any process ratio is higher to lower. So alpha, that is your explosion ratio. Is nothing but alpha is equal to higher pressure to that of lower pressure, P2. And P3 is nothing but your maximum pressure in the cycle. P max by P2. Okay. I hope this much is clear. Now, what is happening when you see the cycle? Let me draw a cylinder. Piston cylinder. If you see this, from point 3 to point 4, point 3 to point 4, if you observe, this is your point 3, and this is your point 4. Okay, point 3 and point 4. So here, first heat is being added at constant volume. Heat has been added at constant volume. And then heat has been added at constant pressure. So you can observe that from point 3 to point 4, your piston is also moving. Okay, from bottom dead center to top dead center to bottom dead center. And finally, your piston comes to the bottom dead center. Okay. Someone's trying to join. Okay. The explosion ratio we have defined. Then we come up with the air standard efficiency finally. Air standard efficiency. Air standard efficiency. Again, air standard efficiency is nothing but your net work done from the cycle to that of net heat added. And this time heat is added 2 times. First at constant volume, then at constant pressure. Okay, constant volume and constant pressure. And if it's a reversible, so we can say cycle is reversible, then we can say that net work interaction is just basically the summation of net heat interaction. Net work interaction is net heat interaction. Okay. So it will be heat addition at constant volume, heat addition at constant pressure minus heat rejection at constant volume to that of heat addition at constant volume plus heat addition at constant pressure. So you can divide this and separate it out. So this is your 1 minus heat rejection at constant volume to that of heat addition at constant volume plus heat addition at constant pressure. Heat addition at constant pressure. Okay. All right. Now, there is, if I say that cycle is reversible, then I write heat rejection or heat addition in terms of net heat interaction is nothing but your that process T times delta T. Okay. So if we say that if our first process, that is our heat rejection, it is constant volume. So CV delta T, and delta T is from which point to which point? Point number 5 to point number 1. Rejection is happening from 5 to. So it will be CV times T5 minus T1. Heat addition at constant volume. So from point 2 to 3, and it is again a constant volume process. So it will be TV times T3 minus T2 plus again heat has been added from 3 to 4, and this is at constant pressure. So T4 minus T3 Tp times specific heat constant pressure T4 minus T. And if you divide by Tv from numerator and denominator, then it will be T5 minus T1 plus T3 minus T2. Cp by Cv is nothing but your gamma. T4 minus T2. Okay. Then Cp by Cv is nothing but your. All right. Is there any doubt still here? Yes or no? Any doubts? Please say yes or no. Hello, I'm audible. Swara, I'm audible. Swara, Gurprasad.
I don't know my voice is reaching you guys or not, actually. That's why I want to confirm it.
Sir, it's clear, sir.
Okay, all right. Whatever I was saying, speaking is was audible to you, right? Okay. If I'm audible, then I can move forward. Yeah. So now we have efficiency in terms of temperatures. Now we want all the temperatures to be in a single form. Okay. All the temperatures to be in a single form. So let us see one by one. First, let's write T2 we will write all the temperatures in term of T1. Okay. We will write all the temperatures in term of T1. Since we know that from 1 to 2, it's a okay. Let's make first the temperature entropy cycle also. Then you will understand more. Uh, one plot was pressure volume. Another plot let us make temperature entropy plot also. TS. Okay. So from 1 to 2, the process was isentropic compression. 1 to 2. Constant entropy compression is happening. So temperature will increase. 2 to 3 was heat addition at constant volume. Okay. Heat addition at constant volume. Let us see. 2 to 3 is heat addition at constant volume. Heat addition at constant pressure. The slope will be less or high. Obviously, the slope of, if I say dq is equal to TdS, and dq is nothing but for constant pressure, constant volume process, Cv dt is equal to TdS. So dt by ds is T over Cv. So slope will be T over Cv for constant volume process. And for constant pressure process, dq is nothing but Cp dt TdS. So dt by ds is T over Cp. And we know that since Cp is greater than Cv, this implies T by C slope of constant pressure is lesser than slope of constant volume. dt by ds of constant pressure. So eventually the slope of the constant pressure will be lesser. So we have to make in term of this. So slope here will be T by 3 to 4 is heat addition at constant pressure. Okay. Now 4 to 1 is isentropic expansion. Isentropic expansion. 4 to 5 is isentropic expansion. And 5 to 1 is again heat rejection at constant volume. So constant volume, that means 2 to 3 and 5 to 1 lines will be parallel to each other. So you have to make the same slope. Okay. They should look parallel. Let me draw once again. Okay. So this will also be T by Cv. Slope will be T by Cv. Okay. So this process was heat addition at constant volume. This process was heat addition at constant pressure. And this process was heat rejection at constant volume. Okay. Now, I was saying that we have the efficiency in terms of this. Okay. Yes, and efficiency in terms of temperature. Now we will convert each temperature. Let us say this equation is A. We will term each the each temperature in terms of T1. Okay. So now we know, since 1 to 2 is an isentropic process, so from that T2 by T1 from the relation is nothing but V1 by V2 to the power of gamma minus 1, and it is nothing but R to the power of gamma minus 1. V1 by V2 is R. So T2 will be T1 times R to the power of gamma minus 1. So we have T2 in terms of T1. Now again we have T3 by T2 is your, so P3 by P2 is your explosion ratio, just now we defined P3 by P2, and it is a constant volume process. So since from gas law PV is equal to RT, for constant volume process, if volume is constant, so we can say that pressure is directly proportional to temperature. Okay, so that means you can write alpha is nothing but T3 by T2, T3 by T2 as just now. Okay, so this implies your T3 will be T2 times alpha, or alpha times T2, alpha times T2. And what is T2? We'll just put here. So alpha times T1 into R to the power of gamma minus 1. So this is your T3 finally. This is your T3. So let us say this is 1, this is 2. Okay. Now we have converted T2 in terms of T1, T3 in terms of T1. Let's go for T4. Okay. So since we know that T rho, your cutoff ratio is nothing but V4 over V3, and it is a constant pressure process. Since pressure is constant, so volume will be directly proportional to temperature from the gas flow. Okay. If pressure is constant, then volume is proportional to temperature. So we can write is nothing but T4 by T3. So this implies T4 will be rho times T3. And now again you have T3. Okay, put this T3 here. So that will be rho times alpha T1 R to the power of gamma minus 1. This is your T4. Again, your T4 has also come. Let us say it is equation number 3. Okay. Now the last part, that is your T5. 4 to 5 is an isentropic expansion process. Again, from the relation we know that T5 by T4 is nothing but V4 by V5 to the power of gamma minus 1. And since V4 is nothing but what will be V4 and V5? How can we convert it in terms of, can we write it like this, rho by R to the power of gamma minus 1? Can we write this? Just now we have we proved it above? Let us see. This was expansion ratio. Okay. So we have just seen V5 by V4 is R by rho. V5 by V4 is R by rho. So V4 by V5 will be rho by R. Okay. From the expansion ratio. So that's why I've written in terms of this. Okay. Rho by R to the power of gamma. Again, we can say that T5 is T4 times rho by R to the power of gamma minus 1. Let's put T4 here. Okay. So that will be rho alpha T1, rho alpha T1 R to the power of gamma minus 1 into rho by R to the power of gamma minus 1. All right. So R to the power of gamma minus 1 cancels out. So it will be rho to the power of gamma, because gamma minus 1 and 1. So it will be rho to the power of gamma alpha T1. So T5 is also in terms of T1. And let us mark this equation number 4. Now let's put all the 1, 2, 3, 4 in equation number A. Equation number A, and our final, let us put first one by one. Put equation 1 to 4 in equation A. So we will be having air standard efficiency 1 minus alpha rho to the power of gamma minus 1. Let me rearrange and finally rewrite. That will be a much better thing. 1 minus 1 by r to the power of gamma minus 1 alpha rho to the power of gamma minus 1 upon alpha minus 1 plus alpha times gamma rho minus 1. Okay, so this is your final air standard efficiency of diesel cycle, a semi-diesel cycle or dual cycle, you can say. Is it clear? Any doubts to anyone? Santosh, is it clear to you?
Yeah, sir. I have one doubt, sir.
Yeah, please ask.
What is mean by T of TF or TS, sir? TS, T subscript S or T
It
subscript
is not
F5?
T5.
Okay, okay. Integral to the power of R.
Rho to the, no, it's not integral. It is rho to the power of gamma.
Rho to
Rho
the
is
power
your
of R.
rho to the power of gamma
Rho
alpha times T1.
gamma. Okay. Alpha T1.
Yes.
Okay. Thank you, sir. Thank you.
And finally, we have, okay, so I'll once again tell that what I've done. So we had an efficiency in terms of temperatures finally. Now we will put all the temperatures in terms of T1. So first T2 from the process, isentropic process, it can be written as in terms of R, T2 is equal to T1 times R to the power of gamma minus 1. Then we know that alpha is P3 by P2, and for a constant volume process, pressure is proportional to temperature. So alpha is T3 by T2. And T3, T2 we have just known from here. So we put the T2 back and we got T3 in terms of T1. Then for the next rho is V4 by V3, that is your cutoff ratio. And this is a constant pressure process. So volume will be proportional to temperature. So rho will be T4 by T3. And T4 can be written, T3 can be written again from here. And you get the T4 in terms of T1. Finally, T5 by T4 is your isentropic expansion process. So it is V4 by V5 to the power of gamma minus 1. Since V5 by V4 is your R by rho from the expansion ratio we saw. So V4 by V5 will be rho by R to the power of gamma minus 1. Again, T4 we know from this equation. Number 3, put this and you get the T5 in terms of T1 again. Put all these equation 1 to 4 in equation A, you will get the final air standard efficiency because in numerator and denominator T1 and T1 will finally cancel out. Okay. So the temperature, it will not be dependent on temperature anymore. This is your final air standard. And it is more or less similar like the diesel cycle. Just in diesel cycle, this term was there, this term was there. Rho to the power of gamma minus 1 was there. Only alpha has been added, okay, in the numerator. Again, this term was also there in diesel cycle. Again, this alpha term has been added. Only the alpha term in numerator and denominator has been added. So this is a trick you can remember that. Yeah, this way we can memorize this air standard efficiency for a semi-diesel or dual cycle. Is it clear?
Sir,
Okay.
alpha and rho are
Alpha is your explosion ratio and rho is your cutoff ratio. Just now we defined above. This is your rho is your cutoff ratio. And
yes,
alpha
rho
is your
cutoff ratio.
alpha is your explosion ratio. Okay. Clear?
Alpha is equal to expansion ratio. Alpha is defined as alpha.
Explosion ratio.
Alpha is equal.
Explosion is happening from P3
Alpha
to P2. Ratio of P3 by P2. Because pressure P3 by P2. Okay.
P3 by P2, no, sir? Alpha?
Yes, I have written here. You can see.
P3
All right. Clear? Can we move forward? Gurpar sir, any doubts you have? Okay. Tennyson, you are trying to speak something? I am not able to. Am I audible to you guys? Can anyone of you confirm me, please? Hello? I don't know. Am I audible? I think I'm audible here. The audio input is fine. Okay. At any point, if you feel that my voice is not coming, please immediately point to me. I don't want the session to be interrupted because of me. Okay. I want that you should all the time be able to hear me clearly. Okay. Thank you. Okay.
Explosion ratio and expansion ratio are different, I think.
Explosion ratio, cutoff ratio, expansion ratio, and compression ratio. Here, 4 terms have been introduced finally. Okay. Compression ratio, cutoff ratio. Okay. Then, oh, my bad. Then expansion ratio, and finally your explosion ratio. Okay.
Sir, please tell me the four ratios. Compression ratio. After that,
Let me just go back. So this is your compression ratio, V1 by V2. Cutoff ratio is V4 by V3. That
V1
is
by
your rho.
V2. Next, cutoff
All
is
these notes, so you will, don't worry, all these PDF notes will be provided. Let me
cutoff
again
ratio.
repeat this thing. So it's good that you guys are writing parallelly with me. It's very good.
Expansion ratio.
But if you, but all these PDF notes are provided by me for all the tutorials. So NPTL team mails you one Google sheet where you can see the recordings of these tutorials are uploaded on my YouTube channel, as well as a Google Drive link is there in that sheet by the NPTL team, where week by week wise, all these PDFs, whatever I'm teaching is exactly this PDF I upload there. As well as if you are not able to access the NPTL team sheets, my YouTube channel name is NPTEL with Varnit, where all these recordings are available. Only those recording links are already in that sheet as well. So both are same itself. So recording this session is being recorded, and on the playlist section for the corresponding course, IC engine and gas turbine, you will see week 1, week 2, week 3, week 4 tutorials. And in each video description, you can see the Google Drive link for the, yeah, Tennyson, if you have no doubts, can you please keep it on mute? I think a background noise is coming. And in each video description, there is a Google Drive link for, again, for the notes of the PDFs. Okay, don't worry about it. All right. Now let's proceed further. We have got the efficiency.
Any simple numerical based on this cycle, sir?
We will come to the numericals. Don't worry. Please wait.
Any simple numerical problem is available for this cycle, sir?
Yes. We will do the numericals also. Don't worry about all those things. We have been doing the numericals. I think you have joined this tutorial session first time. So we have been doing numericals for the each process cycle. Don't worry about that. Okay. All right. Now, let me add a note point. So in this cycle, I skipped the one point which I need to mention right now. That in petrol cycle, the maximum temperature is higher than the diesel cycle. That's why there is a need of a spark in the, because that's why it's a spark ignition engine.
Sir,
Because
your voice is very low.
okay.
Can you increase your voice, sir? Could
Now
you
I'm
please
audible. Hello, am I audible now?
audible, but voice is very low.
Okay, just hold on. Let me disconnect my. Am I audible now?
Yes.
Okay.
Now voice is.
All right. So I was saying that in petrol cycle, the maximum temperature is greater than the diesel cycle. Why? Because in the petrol cycle, first thing is that the self-ignition temperature itself of a petrol is high. That's why you need a spark, external spark for the fuel to burn. And where in the petrol cycle, the net heat interaction is nothing but equal to your net internal energy, because work done for a constant volume process is zero. So when you add the heat, all the heat added is only converting it into a adding as a temperature. Okay, whereas in a diesel cycle, the net heat interaction is sum of internal energy plus work done, because process is you can say constant pressure process. So there some work has been done as well. The internal energy of the system has been changed, as well as the net. So let me write point by point, then you will understand. First, let me write the point of the note. Point number one is that petrol cycle or Otto cycle has maximum temperature greater than diesel cycle, because first reason is that this is a point. First reason is this: in Otto cycle, net heat interaction is du plus dw, where dw is nothing but your pdv. Okay, and when you are adding the heat at constant volume, the change in volume will be zero, so it will be cv times dt. So net heat interaction is basically rising the temperature. So all the heat added is increasing the temperature. Okay, whereas in diesel cycle, the net heat interaction is du plus pdv. Here volume changes not because the process is not zero, because the process is constant pressure, so dv will be there. So here heat is converting into temperature rise as well as work interaction. Okay, second reason is that, first reason is this, second reason is that since net heat interaction is mc dt, so if the process is constant and constant pressure, so c will be cp, and for constant volume c will be cv. And since we know that cp is greater than cv, so more the cp, less the temperature rise. More the cp, less the temperature rise for same heat addition for both the cycle. For why I am saying that? Because if you see this relation which we have derived here, cp value is higher than cv value. So gradient will be for a dt by ds for a volume is higher than that of pressure. So change in temperature will be higher in case of constant volume compared to constant pressure process. Okay. All right, I think this might be clear. Now we come to this equation, that is your air standard efficiency of a diesel, semi-diesel or dual cycle of a dual. Let me write here. Air standard efficiency of a dual cycle. Now if you see here, the dependency is on, of the efficiency is on R, that is your compression ratio, rho, the term gamma, and the term alpha. Okay. Now we will see that which value affects the efficiency. Okay, air standard efficiency one by one. Let us see. So let me write again the air standard efficiency of dual is nothing but 1 minus 1 by R to the power of gamma minus 1 alpha times rho to the power of gamma minus 1 by alpha minus 1 plus alpha times gamma rho minus 1. So if you see here, it is dependent on the term R. So if my R increases, the compression ratio increases. If this increases, the whole term decreases and the efficiency finally increasing. Okay. If my denominator increases, the whole term decreases, and it's a subtraction process. So 1 minus value has been decreased, and the efficiency will eventually increase. So with increase in R, we can say that with the increase in R, our efficiency also increases. Okay, efficiency also increases. Now, if we see the other term, that is gamma. Let me write here. If you see, gamma is nothing but Cp over Cv. So if we increase gamma, gamma is nothing but Cp over Cv. So how can this be increased? If you decrease Cv, your gamma will increase. And if you increase the gamma, again gamma is in denominator here, okay, explicitly. So if you increase the gamma again, this whole term is going to decrease and efficiency again going to increase. Okay. So we can say that efficiency again increases. Third term, that is your alpha, explosion ratio. So there is no dependency over the explosion ratio. Why? Because explicitly alpha is in numerator also and denominator also. So whether you increase or decrease, it doesn't change. Efficiency doesn't change. So there is no effect. Am I audible? I don't know. Am I audible? Let me see. Am I audible? Hello?
Yes, sir, audible.
Okay, great. Let me go back. So we have seen the three terms and their effects, that is R, gamma and alpha. Okay, R, gamma and alpha. Next, the last term, that is your rho. Now rho has a very drastic effect. Let us see. The next term, that is rho, that is your cutoff ratio. So when your rho increases, what happens? If you see in this term, rho is in numerator as well as in denominator. But the question is, in the numerator is in terms of power of gamma, and gamma itself is greater than 1 always. Okay, so it has a higher power in numerator compared to a lower power. In denominator, the power of gamma is 1, whereas in the numerator the power of is gamma. Okay, so rho to the power of something which is greater than 1, it has more influence. So again, numerator value will be higher compared to the denominator, and eventually if this whole term is higher, then efficiency is going to decrease. 1 minus some higher value will be decreasing. So let me write here. With the increase in gamma, efficiency basically decreases. Now let us understand in one graphical aspect as well. When you increase the gamma, okay, let me see. I make a graph. So if you see, this is a pressure volume plot. So initially, if we say for a diesel cycle, how does it look like? The diesel cycle used to look like this. Okay, if you have seen the previous tutorials, 1, 2, because heat addition is only happening at a constant pressure. Okay, whereas in this dual cycle, now you are adding heat here as well at constant volume, then at constant pressure, and then finally you are expanding and rejecting. Okay, so this is your dual cycle. So what has happened? You have increased the cutoff. Earlier cutoff was happening from this point to this point. Now cutoff is happening from this point to this point. Okay. All right. So if I say, if you just observe, they are not inclined in the same level because you have to make these lines parallel to each other. Okay. And if in the graphical aspect, if you see, by increasing the gamma, basically, let me again make this, you are increasing the gamma from this point to this point, and now this is your final process. So earlier your gamma was from this to this, now your gamma is from this to this. Okay. If you increase the gamma, what happens? Why it's not going back? If you increase the gamma, then net extra amount of work is, what is happening to this? You are basically, what you are doing, you are providing more fuel. Cutoff, rho is nothing but your cutoff ratio. So from this point to this point, earlier you are providing fuel from this point to this point, now you are providing fuel from this point to this point. So you are providing more fuel. That means fuel supply is more, load has been increased on the engine. So eventually the engine needs to generate more power. And if some more power is being generated on the cost of more fuel, that engine is not efficient engine. Okay. In a less amount of or same amount of fuel, if you are able to provide more power, then you can say that engine is efficient. Not when fuel supply is also more, then you eventually fuel is your economic resource. It's only limited in the nature. You cannot waste it. More the amount of fuel you provide, more the amount of power you can generate. But on increasing the gamma, basically increasing the rho, basically the cutoff ratio, you are providing more amount of fuel into the system in the engine, and that increases your load over the system. Okay. So if you see, this is the net extra work, the red line, the extra work or power extra. Okay. This implies load on the system is high. This implies fuel supply has been increased. So efficiency will eventually decrease in such scenario. Is it clear? In physically relating to the system, is it clear or any doubts? Hello, I'm audible to every one of you. Guru Prasad, am I audible?
Audible, sir. Can you increase the uh, your speakers 70%? Can you increase your 90%?
That's a battery sign actually. Okay.
Sir, here power will be increased with the increase of rho,
Fuel supply
and simultaneously fuel supply is also increasing, but the efficiency, uh, if
will
powering
decrease.
power with the uh, uh, increase in power and increase in fuel supply, if the increase in power will be more, and compared to the increase in fuel supply, then it may be increase in the efficiency also.
So that is what ideally we want actually. Without increasing the fuel supply, we want more power to be generated, right? But here what we are doing, when we are saying we are increasing rho, that means we are providing more fuel supply. So if you provide more fuel supply and get the more power, that doesn't make any sense, right?
How much power is increasing and how much fuel supply is increasing? We can't say correctly now. The ratio of increase
We
in
can't
power supply to ratio of increase in fuel supply, how can we compare and say that efficiency is decreasing?
see first from the mathematical relation, as I've told, that rho to the power of gamma here in numerator,
Yes.
rho is in terms of power compared to the denominator. So overall the
Yeah.
numerator term is higher. So this whole term is higher and efficiency decreases. That was a mathematical aspect to understand. Then there is
Yes.
a
Based
physical
on that,
aspect
we
to
can say, but based on this diagram,
Yes.
power is also increasing and fuel supply is also increasing.
Yes.
So
So what
based
we
on
have
this,
done, when I'm
uh,
saying that I'm increasing my row, so
uh,
earlier my row was from 1 to 2, okay, from
mm,
this position to this position.
mm,
Now I have increased the fuel supply for the system, okay, from 3 to
yes,
4, okay. If I increase more fuel supply in the system, and for why I am trying to increase the fuel supply, basically someone will increase the fuel supply when the load over the system is higher, okay. That means you want a more power to be generated. If I would have said that without increasing, if I say that, let me draw another, use another color, without increasing the cutoff ratio, I would have been able to generate the same higher power, this is this region, without increasing, then this green engine will be more efficient. But what I am saying currently is that I am trying to increase my fuel supply from 3 to 4, and now I am getting the power output from the system. So from my current situation 1 to 2, I'm getting the net power output to be more, because fuel, I'm providing more fuel supply. Why? Because I want more load. So in that scenario, my engine is not efficient. Efficiency is decreasing of my system. Whereas if in the same ratio from 1 to 2 or 3 to 4 would have been the same, then my engine efficiency would be better. So that's what scientists try to do, or engineers try to do. Okay, is it clear?
sir.
Yeah, okay, thank you. I hope I was able to explain. So we don't want all the time. Okay, now it won't undo much.
Sir,
So let us do. Yes, any doubts?
sir,
Anyone else? Yes, yes, Santosh.
sir.
Please say.
Why you have been marked eta e will goes down. What is mean by LH? You did before you say the name. I will note it down. What is mean by L?
Which
Name
L?
of the what?
Which L you are saying?
Integral symbol. If I'm not sorry, it's not integral symbol, but I don't know if I forgot it. Can you please tell the name?
Eta, sir, you are asking about eta, na?
No. Left side of eta.
That
There
is
is
This
rho.
one?
reference.
That is
Compression ratio.
that is rho, sir. Rho
No,
is
no,
cutoff ratio. Left side
no.
Rho
rho.
is cutoff ratio. Sorry. Yeah. Rho is cutoff ratio.
Okay, okay.
Right
Cut
side
off.
is eta is efficiency, sir.
Efficiency. Okay. Yes.
Left
Thank you.
Okay.
side left side symbol sir has written rho, that is cutoff ratio. Right side symbol
Cut
sir
off.
has written eta, that is efficiency, sir.
Yes.
Okay, thank you.
Yeah. Okay. So I have again made the diagram. It was not getting undo. And 2, 3, and 4, and 5. So this is your extra net power generated with the cost of fuel supply. So that means fuel supply is increased. This implies load is increased. This implies power has been generated more on the cost of fuel supply. All right. Next point where I was. So as fuel is same for diesel and dual cycle engines, hence it is called as semi-diesel cycle. Another point, as fuel is same for diesel and dual cycle engines, hence it is called semi-diesel cycle. See you. Okay. All right. Now let's come to the process of heat addition in detail. Okay. So we are saying in our cycle that heat, again, if we go back and see our cycle once again, so we are adding heat first from 2 to 3 at constant volume, then at 3 to 4 at constant pressure. Okay. So why we have chosen this order, first at constant volume, then at constant pressure? Why not first at constant pressure, then at constant volume? Okay. This can also would have been done. One could have think like that. But there is a reason behind that. That why the constant volume is happening first. Let me write here. I think someone is on unmuted. Let me see. Okay, I think Good Prasad again. A voice is coming from background. Voice is coming from your end. I see. Can you please keep on mute? It will be helpful. Okay,
Here
thank
you
you.
have to mute now, sir.
Yes, yes. Actually, a background noise is coming. What is
Ah,
the advantage of dual cycle compared to diesel cycle? Yeah. So as I stated first in the very first point, that I think you joined late, Tension. So the first point is that diesel car, it can be used in the diesel cars first thing. Okay, because a diesel cycle is a very, as I told, that the engine is quite very heavy if you see for the trucks or a very heavy machinery like in railways. Okay, so railway engine or a truck has a very high diesel engine in a size and heavy engine as well. But if I want to use my diesel engine in my cars, okay, I can use this semi diesel or dual cycle first thing. Second thing is that in the cars I want a higher speed as well as more torque. Okay, so diesel engine are preferred in such scenarios where the cycle speed also increases because you are providing heat addition at constant volume as per Otto cycle, then at diesel cycle as well. Okay, all right, now let us see to the reason for the order. Reason for heat addition order in a cycle, dual cycle. Okay, so heat is added. Yeah, okay, welcome. Heat addition. So first heat is added at constant volume, and then secondly heat is added at constant pressure. So there are two ways. First is practical way, second is theoretical way. Practically, let us understand. If I have a piston cylinder arrangement for TDC to BDC, okay, my cylinder went from BDC to DDC. Okay, now I am providing some fuel inside it and adding a heat, but because of the compression, okay, temperature has been added. If I want to say that my heat is added at constant volume, my piston should remain in this position. Okay, instantly at this position. So if the immediately I can do that because my volume velocity is zero at the TDC. Okay, top dead center, and the volume at that instant is also constant. I can immediately add the heat. But if I say I first add heat at a constant pressure and then I'm trying to add the heat at constant volume, is it possible to stop this piston in the midway? First, if I say that heat is added at constant pressure, then I am saying that heat is added at constant volume. Is it possible? No. It is impossible to stop this piston when it is moving from TDC to BDC while the uh, power stroke. It is possible to stop that piston rotating at such high speeds, okay, running at such high speeds, to add at a constant volume at that instant. You never know that how fast this piston is going down, but we know the velocity of the piston is zero at the dead centers comparative to the middle. We don't know what are the velocities. So one practical way is to say that, or physical way is to say that it is impossible to stop the piston in the midway. We cannot do the process of heat addition at constant pressure first and then volume first. It's always have to be volume first, then pressure. Okay, let me write this. So practical way to understand is that it is impossible to stop piston midway. Okay. Second, in theoretical terms, we can say that work done, theoretical or graphical terms, I'll make a graph also. In theoretical terms, the work done for heat addition at constant volume and then heat addition at constant pressure is greater than work done for heat addition at constant pressure than heat addition at constant volume. Okay. Why? Let us see. Let us make this graph for this. Then you will understand in a much detailed manner. So this is my PV plot, and area under the pressure volume plot gives us the work done. So if I am saying first my process from 1 to 2, then I am saying my heat addition is happening at constant volume, then at constant pressure. Okay. Okay. So we get some work output from this cycle. That is our network output. This is our network output. Okay. Then I say that my next cycle will be like, first I go from 1 to 2, then I add the heat at constant pressure 3 dash, and then I add the heat at constant volume 3 to 4 dash. So the net work output will be for this cycle will be like this. So this cycle is looking something like this: 1 to 2, 2 to 3, 3 to 4, and 4 to 5, and 5 to 1. This is your net cycle. So what you observe that the net work output, this is a loss of work happening in this cycle. Okay, so that is why loss of work. That is why work done is higher when you add heat at the constant volume than at constant pressure. So let me follow this line to show both the processes. Okay, is it clear or any doubts to anyone? So I'll write the points as well. Practically, it is impossible to stop. And I hope that everyone is solving the assignments, weekly assignments, which is available on the portal, Swayam portal. Okay, so you have to be regular if you have registered in the course, and especially for the exam, you have to submit the assignments on time so that you get passed and for the certificates. Okay, practically it is, and even if you are not paid the registration fees and just registered in the course without certification also, you should do those assignments, and I expect that after learning all these through the tutorials you will be able to do, and obviously from the lecture videos of the professor on the portal as well. Practically it is impossible to stop the piston midway for addition of heat at constant volume. Okay, and then if heat addition is happening at constant pressure is first, then area under in PV graph, pressure volume diagram. Someone has tried to join. Let me see. Okay. Area under the PV graph is lesser compared to if heat addition at constant volume is happening first. Okay. Then next point, heat addition at constant volume is less than heat addition at constant pressure. We have seen because after compression, another way, because after compression, already pressure is inside cylinder is high. Okay. So when I'm saying that, if I add first 2 to 3 heat addition at constant volume, then already the pressure is quite high. Okay. And then at same pressure, I provide the heat. But if I do heat addition at constant pressure first, then temperature will eventually rise. We have seen from the TS plot here. Okay. Because you are providing heat to the system, the temperature is going to rise eventually. Okay. And then if you again add the heat in the at constant volume, then the temperature will be too much high. Okay. And the pressure will also be very high. So temperature and pressure both will be high at that point. Whereas initially 2 to 3 only temperature and pressure were initially high, then at same pressure you added the heat. But if you add the heat first at pressure and then again at volume, then temperature pressure will be extremely high, that can burst the cylinder. Okay. Explosion of the cylinder can happen, which is very dangerous. Okay. Let me write that point. Inside is already high, that is your R dual. Compression ratio of dual is nothing but 12 to 16 has been reached. And if we add more heat, at constant volume, then cylinder will explode. Okay. And one point to note here is that experimentally it has been observed that for maximum efficiency, experimentally observed that heat addition at constant volume is nearly 1/3 of heat addition at constant pressure. Okay. Any doubts? So that the stresses in the cylinder are balanced. Okay. And there are less vibration and noises as well. Is it clear? Or any doubts in understanding this concept? The order of the heat addition.
Sir, you have told that practically it is not possible to stop heat addition, some portion of heat addition at constant volume and some portion of heat addition at constant pressure. Practically, how we are achieving that heat addition in two phases, sir?
So as I said that it is impossible to stop the piston midway. So when you want the at the heat addition at constant volume, you don't know at which position you will be.
Practically, what is happening inside the cylinder for heat addition to take place firstly at constant volume and then uh, constant pressure? How
Yeah.
is it going in the cylinder by to follow these heat addition processes? Some portion of heat addition at constant volume and another portion at constant pressure.
So
How we are achieving that task in the
so
uh,
individually, I have explained these processes in detail in my previous
sir?
tutorial. But I'm saying that individually for Otto cycle and diesel cycle, I have explained these processes in very detail in my previous tutorial. But I'll give you a glimpse once again that how first the constant volume is happening, we are able to achieve. So this is my piston at TDC, and I have a fuel injector here. Okay. So at that instant itself, I am providing the fuel inside the and already the temperature is very high because of the compression from BDC to TDC. Okay, so fuel will start igniting. Okay, and even the chemical process of hydrocarbon I have explained, hydrogen and carbon I have explained in very detail in my previous tutorial. So for much detail you can see that tutorial, but I'm just giving you a glimpse. So first, at constant volume, the heat has been added by providing the fuel. Now the piston is moving constantly, okay, from TDC to BDC and BDC to TDC. So now the piston will try to move back, move downward. So when the piston is trying to move from position A to position B, the fuel supply is still there, okay. Fuel supply has not stopped. So here the pressure has been maintained at that instant, and the heat is again added, because once at TDC the piston has reached the pressure is maximum at the situation, and when it is going down, the cylinder inlet valve and exhaust valve both are closed at that point of time, so pressure is still maintained, and this A and B positions are not very high, these are very minimal, you can say in very millimeter, very less. Okay, so still the fuel supply still happens, and at that pressure itself you are able to supply the fuel, and because of that heat is being added at that, heat addition is happening at constant pressure. Okay, is it clear?
Uh,
Okay.
uh, Sir, heat addition at constant volume means and heat addition at constant pressure. Practically, I couldn't understand the difference between heat addition at constant volume and heat addition at constant pressure. Practically, how is it happening? Can
So
you?
you tell me that at TDC the velocity of the piston will be what? When the piston has reached the top dead center, what will be the velocity?
When the piston reaches to top dead center, what are you, sir?
What will be the velocity of the piston?
What will be the
Velocity
almost zero?
almost zero. That means your
Oh,
piston has just stopped at that position, and at that position itself you can provide the fuel. Okay, the sensor
o-
or the actuators where electronic system can sense that my piston has reached at the top dead center, I will immediately provide the fuel into the system. That means you are adding the heat into the system by providing the fuel, because temperature is already high, so you have provided the heat at the constant volume. At that instant the volume of the cylinder is constant, and at that instant itself you have provided the fuel into the cylinder. The heat has been added into the cylinder at constant volume. Now piston is now moving itself, because the acceleration direction has been changed. Although velocity is zero, but acceleration direction has been changed because of the presence of inertia, and we have a flywheel. As soon as the direction of the acceleration changes, the piston still goes downwards, and the fuel supply is not stopped. Fuel will still be supplied from that position, and then the pressure has been maintained constant, and that's why we are saying that the heat is added then at a constant pressure. Although everything in detail I have explained in my previous tutorials, you should once go back and just check out. Okay, is it clear?
okay, okay, sir.
Okay, yeah. All right. Now let's come to the energy transformation calculations. Very important concept for. All right. So again, our fuel is nothing but hydrocarbon. That is hydrogen and carbon, and you mix it with the air. That is, you are doing the oxidation of that hydrocarbon. So we have a hydrocarbon. You do the oxidation, and in the output you get H2O and CO2 plus some calorific value of hydrogen plus calorific value of carbon. So what you have done, the fuel. This was your fuel. Let me use this color. Here, chemical energy was there of the fuel, and it has been converted into thermal energy. Okay, thermal, by providing the heat in the system, thermal energy. Okay, that is your calorific value of fuel. Okay, so basically the conversion has happened from chemical energy to thermal energy, and finally this is being converted to a mechanical energy by rotating the piston and crankshaft. Mechanical energy by displacing the piston and rotating the crankshaft. Here you have piston, let me write, which is reciprocating, and the wheels which are rotating finally from the crankshaft, plus wheels. So this is reciprocating, and this is rotating. Okay, all right. So reciprocating has a power that is force into velocity, and rotation has a power torque into omega. Okay. Now we need to do the time analysis. So basically we have again converted that thermal energy into a mechanical energy. So this is the whole process what is happening here. Let me use this. So first, chemical energy, by burning the fuel you have converted into a thermal energy, and that thermal energy has been converted into displacement of the piston, and that piston displacement has been converted into a rotary motion of the crankshaft, which rotates your wheels. Okay, which converts the energy into a mechanical energy, thermal energy into mechanical energy. All right. Let me write one point here. The total amount of thermal energy or power available from the fuel, that is your CXHX, your hydrocarbon, due to combustion of 1 kg of fuel mass is termed as calorific value. Okay. Now let's do the time analysis. So again we have a piston cylinder arrangement. And this is your position of TDC. Okay. The piston has moved somewhat from TDC and it is moving constantly. Connecting rod, crank rod, and this crank rod is rotating. Okay, with the velocity omega. Let's suppose there is a spark provided. So what is happening? Let's say there is a camera which has been attached here. Camera. Okay. Let me write again. I'm doing the time analysis. So this is your clearance volume VC, and from here till here it's your swept volume Vs. Okay. So from top dead center to bottom dead center, what is actually happening in the piston cylinder? And it is, if you see, this position is your TDC and this position is your BDC. Okay, on the crank rod, and we are seeing that our engine is running at constant velocity, not constant not any variable velocity. So alpha, that is, it will be 0. This alpha is your angular acceleration. Okay, the angular velocity is constant, so angular acceleration will be 0 of that system. Okay, so what is happening from TDC to BDC? Let me make, this is your TDC, this is your BDC, and let us say this is some the midpoint, midway. Okay, so initially when the piston was at TDC, the velocity was 0, but as due to the presence of inertia, the piston is moving downwards. So for some amount of length, the piston will start having increase in the velocity. So let us say we got a snapshot and we were able to see that till this length, our velocity will be v1 L1 by t. Okay, no, let us do half by half, not a particular length. Okay, so let us say in the midway we have moved a length L1, so velocity will be L1 by t. Okay, then from next length till the midway, the piston is now again still having a higher velocity. It's not yet reached the bottom dead center or even the midway. So piston is gaining its velocity. So from this position to this position till the midway, the velocity will be v2, that will be L2 by t. L2 by t. For the same time I'm seeing. First time I captured, the same time I captured once again. The distance covered will be L2. Okay. The same cycle will repeat when it will go from midway to the bottom dead center. Again, the velocity will still remain same from the midway to this position. V2 will be L2 by T, and finally, again the piston will stop because of the end of the bottom dead center presence. Then V1 will be same, that is L1 by T. And why I am saying that my V2 will be higher than V1? The V2 will be higher than V1. So basically, the piston started from a 0 velocity, started to gain a velocity, until the mid, from L2, for the L2 region, the velocity was maximum at the middle point. Same velocity it carried forward till some position L1, towards the end of the L1 near the BDC, and again the pistons tried to stop for the remaining length L1. Okay, and I have specifically mentioned that my system is rotating at a constant velocity, angular velocity, constant angular velocity. Okay, constant angular velocity, not constant velocity. So my V2 will be higher than V1. V2 will be higher than V1. So if we see, this was the reciprocating motion of the piston. What was happening on the rotating part? That is your crank rod. So if I see my crank rod, let me make, in the meanwhile, my crank rod from TDC to BDC, from my first 45 degrees, my time will be for this much t. The velocity was increasing of the, that is your V1 velocity will correspond to this for the next 45 degrees. For the same time, the reciprocating velocity will be higher, but the angular velocity of the system is same. Okay, so if I say that in this side, where my velocity is becoming 0 but acceleration is there in the system, first the system was accelerating from this position to this position, accelerating, and then it was deaccelerating. deaccelerating. Okay, and these are the points where velocity was 0 but acceleration was there. So these are the points where the system is experiencing jerks. Okay, these are the jerk points. These are my jerk points. Jerk points. Okay, and here the noises and vibrations are maximum. So here velocity is 0 and acceleration is maximum at the jerk points, and vibration and noises. Vibration and noises will be there. Okay, so this is what is happening in the mechanics point of view. So conversion of rotatory into reciprocating motion I have tried to explain. Okay, or reciprocating into rotatory. Okay, vice versa. Okay, so this is basically conversion of rotatory to reciprocating motion. How I was able to achieve? Because I have put the camera at that instant where I'm sensing this, where I'm capturing the points, and here I have a sensor here which detects that my system has reached to the TDC or not. Okay, all right. Now we know that angular velocity is nothing but angular displacement to that of time. Okay, for a constant velocity system where acceleration is 0. So let us take an example. If I have a engine which has 24 rpm, it is at a position of 24, running at a position of 24 rpm, and the engine is 4-stroke. What will be the time of the cycle? Can anyone tell me time of the cycle? Am I audible? Hello? Santosh, Guruprasad, am I audible?
Audible, sir.
Audible,
Audible.
sir.
Okay, okay, great. So can anyone tell me what will be the time of cycle for a 4-stroke engine? We know
40 seconds.
Yeah, please go ahead. In term of fraction, you can tell me final answer. Yes.
20 seconds or 40 seconds?
20
20
or
seconds, sir.
20 or 1 by 20. 20 seconds is very high. If one cycle is taking 20 seconds, so our car is not going to move.
Okay.
It will be very slow. Okay. So
Omega
let us
is
see.
theta by t. Omega, okay, theta, angle displacement.
So let me write. So theta of cycle to that of omega of cycle. Okay. So theta of cycle is nothing but for a 4-stroke engine, how many complete revolutions will happen? There will be 2 complete revolutions will happen. First, from TDC to BDC, then BDC to TDC. TDC to BDC happens a suction stroke. BDC to TDC happens a compression stroke. One complete cycle, that is 360 degrees. Then again TDC to BDC for a power stroke, and then BDC to TDC for an exhaust stroke. the second 360-degree. So for a 4-stroke engine, 2 complete cycles happen. Okay, this thing I have also explained in my initial tutorial. So 2 complete revolution, that is 2 times of 360 degrees happening, and it is in degrees. I want in radian, so I'll multiply by pi by 180 degrees. And what is omega of cycle? It is given 2400 rpm, but I want radians per second, so I have to multiply. What is omega in radians per second? It is 2 pi n by 60. So 2 pi n is 2400, for per second it will be divided by 60. So this will come out to be 1 by 20 seconds. Okay, so time of my cycle is 1 by 20 seconds. Okay, if you solve it. If I ask what is time for the stroke, now
Sir,
please tell me. Yes.
no. What is
Yes.
mean by? Can you please explain 2 by into 2400 divided by 60?
Let me write here. Since omega in terms of n is written as 2 pi n by 60. N is given as 2400 rpm.
Oh. Number of cycles. N means denoted as n number of cycles.
No, n is revolutions per minute.
Oh, 2000 or 2400 RPM of engine of an
Yes.
engine.
Yes.
Okay. 2400 RPM of engine is while in start idle condition or in through running condition.
Running condition. I'm talking about
Running
at 2000.
condition.
Yes.
Oh, sir. If you start the vehicle around, it will run at 2000 to around 1,500 to 2000 RPM. How it is possible?
So just
What is the speed of?
pedal the
What is the
accelerator.
speed of?
That is what I'm saying. If you pedal the accelerator lightly, then it will reach 2000 to 3000, 3000 to 4000. I'm just saying at a particular instant I'm talking. As soon
Okay,
as the
okay.
engine has started, I'm talking at a
What
particular
is,
level.
what is an average speed you have been taken and you have been calculated?
Which average speed?
2400 in
This is
just
given
in
in
10 kilometers.
just I'm saying that it's an example that I'm taking a n as 2400 rpm for a 4-stroke engine. Tell me the time of the cycle.
Okay. You're asking
Okay,
about the time of stroke, sir, now?
Now I'm asking time of stroke. Yes. Time
1
of
by
cycle I
80.
have
1 by 80 seconds, sir.
1 by 80. Correct. 1 by 80 seconds. So again, a stroke will cover only 180 degrees. Okay. Like if I'm saying from TDC to BDC, from TDC to BDC only 1 by 180 degree covers. Okay. So theta of stroke to that of omega of that is given to you. That is in terms of RPM. So omega will always be constant. It is not specific to a stroke or a cycle, because I'm saying that my engine is running at 2400 rpm, constant constant angular velocity. So theta of stroke is 180 degrees into pi by 180, converting in radians, and omega is given as 2400 again, 2 pi n by 60. So it will be 1 by 80 seconds. And to verify it, one stroke for a 4-stroke engine is taking 1 by 80 seconds. So 4 strokes will be 4 into 1 by 80. So it will be 1 by 20 only. Okay. I hope this is clear to everyone.
Or in another way, time of cycle already we have calculated that we got
Yes.
as 1 by 20 seconds. Since
Yes.
one cycle consists of 4 strokes, so time of cycle is 1 by 20 seconds. 1 by 20 into 1 by 4
4.
will give
Correct.
you the 1 by 8.
Yes. Right. Okay.
Like
Thanks.
that also we can calculate.
Yes. Yes. That's also the right way. Okay. Now let's come to the second part. So this was the first part of the energy transformation calculation. Let me write part 1. Now let's come to the second part of it. Part 2. Now you have made a pressure volume diagram. Let me. Someone is trying to join. Okay. So we have made a pressure volume diagram. So let us say it is a Otto cycle only. 1, 2, 3, 4. Two, three, four. So this was your net work output which you were getting. Okay. So this work done is also called as an indicating power or reciprocating power, okay, of the system. Or work done per second is your power only. Okay. So indicated work done per second is called your indicated power. Again, someone is trying to join. Okay. Let me, yeah, I have joined. So this is your indicated work done per second is called indicated power, indicating power, or you can say because this diagram is made from the reciprocating motion of the piston. Okay, reciprocating power. Okay, so this from the PV indicated diagram. Why I'm saying indicating? Because it's a diagram, PV diagram, which is indicating your network output of the system. And if you do per second, it is the work done per second, that is your power. Okay, so I can write here that PV diagram, indicated diagram, PV indicated diagram. Okay, or only indicated diagram also you can say. Okay, PV indicated diagram or indicated diagram. Now we have understood the concept of mean effective pressure in our previous tutorial. So what was the mean effective pressure? It's an hypothetical or theoretical pressure which gives the same power output for the same displaced volume. Okay, so indicated in power, IP, let me denote it through P, can be written as mean effective pressure, indicated mean effective pressure. When I'm talking about indicated power, so eventually I want to talk about indicated mean effective pressure times swept volume. Okay, times swept volume. Next power is our, so from the reciprocating motion, we are getting a rotary motion. Okay, so let me draw a piston cylinder arrangement here. TDC. This is your PDC. This is your piston. So here you are providing indicating power IP, okay, for the reciprocating motion A, and this piston is connected to connecting rod and then crank rod and finally to a crankshaft, and this crankshaft is connected to the wheels. Okay, wheels. So whatever power you get on the wheels, if you whatever power I was getting on the wheels, these wheels were rotating at a constant velocity omega, or whatever the velocity, not constant, I'm saying whatever the velocity omega, and there are brake pads here, brake shoes or brake pads available with us. Brake shoe. So if, and this is a brake drum or wheels, brake drum. Okay, if I suddenly apply a brake shoe, so that is the amount of power I can calculate through a tachometer as well. If you see in your laboratories, there is a tachometer where you can measure the RPM, okay, of the wheels. So from suddenly stopping the whole wheel, I'm getting my frictional force FB from the brake, FB, and that is nothing but frictional coefficient times normal force. Okay, frictional coefficient times normal force. So normal will be, and coefficient will be this. So friction force basically. And if I show you a side view of it, let me show the side view of this brake drum. So the wheel was rotating at omega. Okay, the wheel was rotating at omega, or brake drum was, and this has a drum radius RD, and we have stopped by applying FB. Okay, let me use same color white here for FB. And earlier it was rotating clockwise, so force was this direction. Okay, so these are basically same when you have stopped at that point. So this is not nothing but your brake force. Okay, and brake force into brake radius is nothing but your torque, R cross F. Okay, so RD cross FB is your braking torque, and if you multiply with the omega, the torque, you get the power of it. So let me write here, FB times cross RD is your brake torque, that is your TV. You all might have done this experiment in your labs. You have a rotating motor and a drum is attached to it, and counterbalance weights are there to stop the brake drum through a brake shoe. Okay, and you have a tachometer in your hand, a laser kind of device which reads the RPMs. So FB cross RD is your braking torque times your omega, which you get through your tachometer, finally gives you a brake power. Finally gives you a brake. So this FB you get from that counterbalance weights. This you know from the geometry. You get the braking torque. Omega you get from the tachometer. So this is your finally brake power or rotatory power as well. BP, or you can say it as a rotatory power. Rotatory power. And this is basically your power output or power delivered by the engine. Okay, this is your, this whole is your brake power is nothing but your power output. Let me write here, power output. Indicated power was the power input to the system through the heat addition, whereas the net output over the drums or the wheels is basically your, from which the car is moving or your vehicle is moving, is your power output or power delivered by engine. Or it is also called as engine output. So whenever you see these terms, these are same. Power output, power delivered by engine, or engine output are same. Any doubts still here? Then I'll write the points for this. Okay, so I'll write the points. You will get a more clarification over it. Someone is unmuted. Please, can you mute yourself? Background noise is coming. So my first point is, can anyone please unmute yourself? Whosoever is mute yourself. Whosoever is unmuted. Expansion of air from P pressure and volume changes. Air or air filled mixture, whatever you can say, because we treat currently this has a, in our assumptions in the first tutorial we said that the working fluid is air. Okay, then work done which is given, that is input to the piston, which is given to piston, or you can say work done by the air is indicated work done. Oh, A lot of noise. Can you please make yourself or I have to mute yourself? Mute you. Ratish, the participant. Okay, I think he's muted now. Alright, so I was saying by the ear is indicated, work done. These are indicated work done. And it is input to the piston. Input to piston and found by indicated diagram or PV diagram. Okay. Second, energy available from shaft of engine is also the energy found by brake mechanism at wheel is known as brake power or brake work done. And this is output from piston. Output from okay. So now we have two powers. So definitely some ratio will come here for the two powers, and that ratio is called as mechanical efficiency of the engine. Till now we were dealing only with the air standard efficiencies. Mechanical efficiency, and it is the ratio of output energy of piston to input. Ratio of output energy of piston to input. That is nothing but your brake power to that of indicating power. Eta M, mechanical energy. Okay, mechanical efficiency. All right. Eta M. So what basically you have done? You have added the heat per second. That is nothing but your mass of fuel, mass flow rate of fuel times calorific value, from which you got the indicating power. Then using the friction power, you got the brake power. Okay, so I can say that this is your FP, friction power, that is energy lost due to friction. Okay, this brake power you are able to achieve at the wheel. Okay, and this indicating power you are getting at piston. Okay, so some thermal energy was provided, so it is heat by providing the heat. So here there will be efficiency of indicating thermal efficiency of the system. Okay, from where, which is nothing but heat added with the and out input power generated, and from input power to the brake power you are getting the mechanical efficiency. From input power to the brake power you are getting mechanical efficiency. This is your mechanical efficiency. So we will define indicated thermal efficiency and brake thermal efficiency here. Okay, so here what you are basically doing is you have a hydrocarbon, carbon is sitting inside and hydrogen is surrounded, being lighter. You have 1 kg of fuel where you say the calorific value. You ignite this fuel in presence of oxygen. On ignition, you got the thermal energies out of it because of the calorific values. Okay, calorific values CV of the fuel, that is in terms of heat addition per kg. So here two efficiencies comes out. First efficiency is indicated thermal efficiency. Indicated thermal is indicating power whatever you are getting to that of heat added per second. Okay, and break thermal efficiency. Break thermal. So it is between break power to that of heat added per second. And this is nothing but your efficiency of engine also. Okay, efficiency of engine, not mechanical efficiency. Efficiency of engine, I am saying. So different terminologies have come now. Okay, you have to remember, you have to go through this tutorial once again so that you can remember that which efficiency is which one. So from this to this, it is indicated thermal efficiency. From this to this, it is sorry, not this to this. From this to this, it is break thermal efficiency. From indicated power to this is mechanical efficiency. Okay, clear? Is there any doubts? Hello, am I audible?
Yes, sir, you are audible.
Okay.
Audible,
All
sir.
right, we will come to the indicated work done. And should I tell this? Okay, let me tell here itself only. Let's come to the part 3. Let's take a few more minutes and complete here itself. So we know that indicated work done per second is your indicated power, and this can be written in terms of mean effective pressure, indicated mean effective pressure into swept volume flow rate. Okay, similarly for brake work done per second is your brake power, and it can be written as brake mean effective pressure into displacement flow rate. So mechanical efficiency is brake power to indicated power, you have just seen. So it is nothing but PBM Vs dot by PIM into Vs dot. So this cancel out. It is ratio of brake mean effective pressure to that of indicated mean effective pressure as well. Okay. Then we have a terminology of specific fuel consumption, but I will relate this later. I think this is for specific fuel consumption. We will come into the next session. Okay. I hope this is all clear till today. And do you have any doubts? If no doubts, do you have any doubts? I hope everything will be clear. But you have to go through this tutorial once again, okay? Because new terminologies have been introduced, and I'll start with the good numericals in the coming session, coming tutorial, and I will also come up with the actual and ideal PV diagrams. So far, we have dealt with the only ideal PV diagram, but how the actual PV diagram works, actual engine works, that pressure volume diagram will also make. So this is all from my side for today. All these notes and the recording will be available via Google Sheet through Nptel team, as well as if you want to see right now. So my YouTube channel name is YouTube is NPTEL with Varnit, where all the recordings will be uploaded, and you can watch in the playlist section for the corresponding course, gas, ice engine and gas turbine. And each video description, you can see the Google Drive link where the PDF of the notes will be available week by week wise. So, and other playlist section, I have different courses which I've taught on the NPTEL as well. Okay, if there is no doubts, so can we end the session now? There's no doubts. Okay. Let me stop the recording.